Hello, welcome to the video lecture for Chapter 4, Part 2. In this video, we are going to be talking about the moon. In fact, we're going to be talking about two major aspects of the moon. We're going to be talking about lunar phases, and we're going to be talking about eclipses. So this picture here, this is a space-based picture of the Earth and the moon's orbit. So they're showing the ecliptic here, which is a horizontal line, and you can see the sun in the back there. Earth has a axial tilt, right, 23.5 degrees with respect to what we call the ecliptic pole. And we see the moon here. Moon orbits the Earth. It does not stay on the ecliptic, though. It has a 5-degree tilt with respect to the ecliptic. And you can see the picture at the bottom there has a to-scale drawing of the Earth and the moon and the relative distance and the orbital tilt of the moon. It's 5 degrees with respect to the ecliptic. That is a very important detail because that means the moon is not typically aligned with the ecliptic, and it's usually above or below. And that produces something interesting when it comes to eclipses, and we'll get to that later in the video. The moon has prograde motion. So we've talked about prograde motion before. It's sort of the normal motion of things in the solar system. As viewed, if we view like the solar system from an overhead perspective, meaning like the same side as the North Pole, things move counterclockwise. That's prograde motion. And so the moon's orbit here is prograde. Now, question for you here. As viewed from the Earth, the moon always has the same side facing the Earth. What does this imply about the rotation of the moon? So, yeah, all throughout humanity, the moon has always looked the same. The same features appear no matter what. And that says something about the moon's rotation. So what do you think that is? The answer here is B. The moon does rotate. We know the moon orbits. So if the moon orbits, it would have to rotate in order to maintain the same side facing us. But there has to be something special about that. We call this a tidal lock. So the orbital period of the moon and the rotational period of the moon are the same. So as the moon orbits the Earth, it rotates through the same angle so that the same side always faces us. So there's a close side to the moon that we always see on a far side to the moon that we had not seen until I think the year 1960 when the Russians had launched a probe. I think it was called Luna 1. That went up to the moon and around and took a picture of the other side of it. So that's the first time we ever saw that, right? So you think about this. If the moon didn't rotate as it orbited, you would end up seeing the various sides of it. But because it does orbit, it does rotate, and it does so in a special way. We call it tidal lock. We also call it geosynchronous. Now that term tidal, right, that was something we talked about in the last video. This is caused by tides. So you might remember me mentioning that the moon slows the rotation of the Earth down. Well, we did that to the moon. But the moon is less mass. It was a more dramatic effect. And it slowed down so much that the moon became locked to us. It's a very common eventual state of any planet-moon system. At some point we'll lock to the moon. I mean, technically speaking, if things could happen indefinitely, then our day would become a month long. The solar system is going to be gone before that. The moon actually will drift away before any of that happens, but that's something that can occur. Other things that are geosynchronous, as I mentioned it at the bottom here, if you're familiar with like satellite cable satellite systems like Dish Network and things like that, when they set up the dishes on your house or apartment or whatever, they're pointed into the sky because they are satellites up there that are geosynchronous satellites. They orbit in such a way and they rotate in such a way that they always have the same side facing the Earth, so they can send and receive, the satellite signals. So it's the same kind of thing. All right, so yeah, it's kind of funny. There's like this almost misnomer for the moon. Pink Floyd made famous the phrase "dark side of the moon." Okay, well, dark side of the moon's not very interesting actually, because we see the dark side of the moon all the time, right? Because of phases. What they should have called their album was Far Side of the Moon. Doesn't quite sound as good, but there was a comic that was Far Side. But anyway, all right. So, how long does this stuff take? Well, there's two ways you can describe this. And you see the word sidereal up there? Sidereal is a word we've used before when we're talking about the Earth's rotation. So there's actually two ways you can describe this. You can see in the picture here, we see our moon in new phase next to the sun on the ecliptic. And the amount of time it takes for the moon to orbit the Earth and come back to the exact same spot that it is relative to the background stars, meaning it's going to be back in the constellation of Scorpius, that amount of time to go all the way around to the exact same spot relative to background stars, 27.32 days is how long that's going to take. Okay, but if you look at the second picture, you'll notice that the moon is not next to the sun anymore, though. So the moon completed a full orbit, but it's not next to the sun. And in fact, the phase of the moon is actually going to not be a new moon. So, and it's actually, and also this 27 days, this is not what we generally associate with like lunar cycles, right? So it's kind of like the sidereal day for the Earth. Like technically the Earth has this particular number that describes its true motion. This is a number that describes the true motion of the moon. However, when we look at the moon, we view the moon with respect to the sun. So the cycles that we associate with the moon have to do with phases and how it gets back to the sun. So, what did the sun do in that roughly month of time? Well, the sun moved along the ecliptic because of us orbiting the sun. So the perspective of the sun changes, right? Now it's in Sagittarius. So there's a little bit of extra time it takes for the moon to catch up to the position of the sun and go back to the same phase it was last time. So that's different. That's called synodic period. That's how long it takes for the moon to go all the way around and then catch up to the position of the sun. That's 29 and a half days roughly, and that is approximately a month, and that's what we generally associate with the cycles of the moon. We call it synodic because synodic means relative to the sun. Okay, so the number that's important for us is the 29.5 because that's how we view the moon. The fact that it technically does a complete orbit in 27.3 days is mostly irrelevant. We don't really see that. We see the phases, right? So that's why this number is more important. Okay, so let's move on to phases of the moon. When we talk about phases of the moon, there are a couple facts that you want to keep in mind to help you understand how phases of the moon are occurring. Fact number one is every object in the solar system, moon included, is always half illuminated by the sun because it's the side that faces the sun. The second fact is the Earth always sees half of the moon, and it's the half that faces the Earth. So when it comes to understanding phases of the moon, you're trying to figure out how these two sides line up with each other. For example, if we look at the waxing crescent phase here, I'm going to draw a line here, and that line kind of splits the moon up into the side that faces the Earth and the side that faces away. And as you can see here, as we look at the moon, The left side is mostly in darkness, and there's a small portion on the right that is in daylight. So the side that is lit up by the sun and the side that faces the earth kind of overlap a little bit. In fact, the picture that's shown in the upper left here is how the appearance of the moon looks, right? And the name crescent refers to that shape, right? So we can kind of see like the moon has to be in that particular spot for those two sides to coincide so that we see that crescent shape. So the phases are really about where the moon is in its orbit. And that really determines, what we're going to see. You look at the top there, first quarter. I'll draw another line there, right? So it's called first quarter because it's the first time we see half of the moon. Okay, we see half of the moon and half of it's lit up. So that's a quarter, right? Half of a half. All right, gibbous phases are caused when the moon starts to get to the other side of the earth with respect to the sun, and then the side that's lit up is more noticeable to us. And of course, a full moon is when the side that's lit up by the sun and the side that faces the earth, they completely coincide. Right? Now, these phases, we say that the cycle of lunar phases starts at new moon. So from new moon all the way around the earth back to a new moon, right? That's the synodic period. That's the 29 and a half days. The terminology of waxing and waning on here, waxing simply refers to the fact that on successive days, if you were to view the moon, you would see the illumination increasing from day to day. And the waning means that the illumination is decreasing from day to day, right? So there's 8 phases in total. We got the new and full, we got 2 quarters, 2 crescents, and 2 gibbuses. Those are officially all of the phases that are on there. So this figure is really good for sort of explaining why we would see different phases based on where the moon is located in its orbit. But you'll notice there's some other information on here that actually is very useful for not only determining, what kind of phase you will see, but you can also determine when and where an observer can see these things. So you'll notice on here I have sunset, sunrise, midnight, noon. And, the sunset person, you can see why they're the sunset person because that's a location that's currently rotating into darkness, right? The sunrise person is rotating into daylight, so that makes sense that those 2 places are sunset and sunrise respectively. Now, we know when the sun sets that the sun is in the western sky. So what I can do here with this figure, I'm going to take the sunset person and I'm going to draw a line that cuts the earth directly in half. And that line is the horizon. So everything above that line is something that the sunset person can see, and everything below that line is below the horizon for the sunset person. And we know that the sun is going to set in the west, so that means the right-hand side is the western part of the sky, and the other side is the eastern part of the sky. I'm going to label it east here. And you can do this for any particular time to determine, what can be seen and where it can be seen. So the sunset person sees waxing crescent in the western sky if the moon is waxing crescent, and a waxing gibbous would be in the eastern sky if the moon is in that particular phase there. It's very easy to determine which direction is going to be east because remember, east is prograde, and if you notice the arrow that indicates the direction that the moon orbits, that's prograde, that's toward the east. So we know that for at least the sunset person, east is on the left and west is on the right. Now, let's change this, though, for another observer. So I'm going to draw a vertical line here, and that's going to represent the horizon for the midnight person. So everything on the left is something that the midnight person can see, and everything on the right is below the horizon. They cannot see that stuff. And then in terms of east and west, the top portion would be west, and the bottom portion would be east. Now, why did I know that, or how did I know that? It's because the bottom portion, it's in the direction of the orbit of the moon, right? So we're going counterclockwise here, down to down. So that would be east. That's prograde. So you could do that for any of these times a day. You just draw a line, you figure out east and west, and you can figure out what can be seen and when and where, right? So let's test that out. Let's do it. All right. According to the figure, what time of day should you never see a crescent phase? Think about that. Answer here is midnight. All right, so let's draw that line again. Oh, that's weird. Yeah, that's the horizon for the midnight person. Where are the crescents? They're below the horizon. That makes sense, right? Because, in order to make crescents, the moon has to be somewhat close to the sun. And if it's midnight, there's no way that kind of moon would be up in the sky in order to see. You can see a full moon. You can see the gibbous phases just fine. The quarter phases, they're on the horizon, so you would be witnessing either them rising or setting, depending on which side of sky we're talking about here. So, yeah, midnight person cannot see crescent phases. Next question. According to the figure, if the moon is in full phase, where would you expect to see it in the sky at sunset? All right, so full phase is on the left here. We have our sunset person here. We're going to draw that line. All right. So what's the right direction here? The answer is C, on the eastern horizon. So I'm going to draw that line. The direction of the motion of the moon indicates east. So east is on the left here. So that's eastern horizon. So as the sun is setting, you look to the east, the moon is rising. All right, great. Next question, last question, a little harder. What time of day would a waning crescent moon appear in the eastern sky? So the waning crescent is down to the right. So what you want to do here is you want to kind of play around with the different times. Think about drawing that horizon, thinking about which directions east and west. The answer here is sunrise. Let's do it. For the sunrise person, let's draw their horizon. Okay, so everything on the bottom are things that the sunrise person can see. They can see the waning crescent, and the direction of motion of the moon is towards the right-hand side. That's east. That's east. And the other side's west, therefore. Oh, I got messed up a little bit. So, you could even do this for the other times here, like noon. Noon can see this phase. Noon can see this phase. Look at this. It's, however, now in the western sky. Why in the western sky? Sunset can't see it at all, and midnight can't see it at all. All right. So really handy figure, right? Tells you, based on where the moon is located, what it would look like, when you can see it, where you can see it in the sky. It's pretty neat. All right, let me show you another perspective of this stuff. So this is an Earth-based perspective of looking at the phases of the moon. And this is sometimes referred to as a stroboscopic image. So let me explain what that means. Imagine you went out and it was a new moon. Right? So you go out when the sun is setting. Obviously, you wouldn't see the moon because it's right next to the sun. There's nothing up there. But if on the next day you go out when the sun is setting and you go to find the moon, you're going to see it right above the horizon. You're going to see this phase on the far right here. You're going to see a little tiny crescent right there. And for the next week, if you continue to go out right when the sun sets, you'll notice that the moon is becoming more and more illuminated, getting higher up in the sky and moving towards the east. That's because it is orbiting the Earth. After about a week of time, it reaches the first quarter phase. So it would be kind of directly south, a little overhead when you see it. The next week after that, it's going to go through the gibbous phases until it reaches a full moon, and that moon would be rising as the sun is setting. This is all the waxing phases. That's all stuff you can see in the evening sky. This is about 2 weeks of time. Now, if you go out again on the next day, you're not going to see any moon anymore because it would start to enter the waning phases and it would not be above the horizon yet. In fact, On the day when it's the full moon, you can stay up all night, watch the moon in the sky. It's going to drift across the sky, and then it's going to start to set. And then you could start observing things in the morning. This is the same kind of picture, but it's for the morning sky. So same deal here. You go out when the sun is rising. For the next 2 weeks, you'll see the moon drifted in its orbit, moving east, again, prograde. It will first start going through the waning gibbous phases, then reach third quarter after about a week. And for the next week, it goes through the waning crescent phases, and then it reaches the new moon, and the whole thing starts over. Right? So that's another way you can sort of visualize where the stuff is located. You could make similar pictures, by the way, for like midnight. It would be all the gibbuses. You could do a similar picture for noon. It would show you all the crescents. So, in fact, the picture for noon is really interesting because if I had the picture for noon, I'd see all the crescents, and I would also see about 2 weeks of time. And some people are surprised. They usually associate the moon with nighttime, and obviously, the moon is more visible during nighttime. But the moon is up when the sun is up quite a bit, like half of its cycle. It's up when it's when the sun is up, but it's crescents and it's not very bright, so it's kind of hard to see all that stuff. All right, so that's it for lunar phases. We're going to move on to our last topic, and that's on eclipses. Now, we have two types of eclipses. We have solar eclipses, and we have lunar eclipses. And what I've done here is I have created a couple different descriptions of these effects. And as you read them, you'll notice that one of the descriptions is more familiar to you because it's what you witness. And the other one, while it's true, it's not how we generally think of eclipses. But we want to describe both of these because it gives us a bigger picture of what's happening here. Solar eclipse. Earth passes into the moon's shadow. So if the Earth passes into the moon's shadow, well, fine, except that we don't really see the moon's shadow, right? It's not easy to see, so that's not how we generally think about what a solar eclipse is. But the other description, moon passes in front of the sun as seen from the Earth, yeah, that's what we generally associate with the eclipse. So the moon's blocking or eclipsing the sun. And obviously, if that's taking place, the shadow is then casting us. But it's not really obvious that there's a shadow that's hidden the Earth. So the second description is the one we kind of think more about. Lunar eclipse. Moon passes into the Earth's shadow. That's actually the one that we do generally more associate with a lunar eclipse. And the reason why is because when the lunar eclipse is happening, we're literally seeing the shadow cast onto the moon. I mean, the Greeks recognized that when the lunar eclipses were taking place, that it was the Earth's shadow because of the way things were supposed to be lined up and the fact that their shadows are curved and Earth is curved. And so it was pretty obvious to them that that's the case. Earth passes in front of the sun as seen from the moon. Well, you'd have to be on the moon to really see that. So we don't really generally associate that effect with a lunar eclipse. But all of these descriptions are true. In fact, I have this question at the bottom here. It says, which one of these is a misnomer? So you might be thinking, what do you mean by that? Well, when I say misnomer, I mean the name of it is not exactly appropriate. Like it's not the right name for what it should be. I mean, we call these things solar lunar eclipses. But if you really think, like literally these terms, eclipse, which one of these things do you think is not really the right name for what's being described? Now, I would say that lunar eclipse is not the right term for it. They're both solar eclipses, right? For solar eclipses, moon eclipses sun. For lunar eclipses, well, it's the Earth eclipsing sun. So it's still a solar eclipse, but you'd have to be on the moon to see the solar eclipse, right? But in both cases, something is eclipsing the sun. Nothing eclipses the moon necessarily. So when we say lunar eclipse, nothing passes in front of it, right? So lunar eclipse is a misnomer because it implies that something passes in front of the moon. And from our perspective, nothing passes in front of the moon. From the sun's perspective, the Earth is passing in front of the moon. So, that, in a weird way, that's kind of a lunar eclipse. But anyway, We give these two different terminologies because it would be confusing to describe these two effects with the same name, right? So, anyway, all right. Now, there's a word on here that's key to helping you understand eclipses, and that word is shadow. Shadow. So we're going to talk about shadows a bit. This picture here illustrates the two types of shadows that objects can create. We have a light source here, it's a light bulb, and we have this obscuring object, this little red ball on the end of a pencil. And you can see that that ball produces two types of shadows. One is called an umbra, which is also called a full shadow, and the other one's called a penumbra, which is a partial shadow. If you put yourself into the umbra and you attempt to look at the light bulb, the red object completely obscures it. You can't see the light bulb at all, right? That umbra is like a cone-shaped region, and it converges down to a point. And that point just so happens to be the exact distance where the light bulb and the red ball would have the exact same angular size. Right? That's what that is. Now, the penumbra is a partial shadow. It's also cone-shaped, but it's a diverging cone. It opens up, and if you place yourself in the penumbra and you attempt to look at the light bulb, the red ball only partially blocks the light source, so we call it a partial shadow. Now, when you typically witness shadows on the Earth, you're almost always observing umbral shadows, umbras. Penumbras are very difficult to see because for the distance that the sun is from the earth and at the distance that things are from where they cast their shadows, penumbras end up being like these super thin boundaries that are almost impossible to see. I mean, the only time I would say that I definitively saw a penumbra is I was in like Yosemite and the sun was coming up over Half Dome and casting a shadow on El Capitan. And you could see the transition from the dark to the light, and that was the penumbra. But that's an extreme example when you're dealing with extremely large things like mountains and things like that, right? So, the Earth has an umbra and a penumbra, right? Every object has an umbra and a penumbra. So when the moon gets into the umbra is when lunar eclipses happen. If the moon gets completely into the umbra, it's a total lunar eclipse, and if it partially gets into the umbra, it's a partial lunar eclipse. The moon does typically get into the penumbra, but that is never important when we want to think about eclipses. And think about why you think that might be, just for a second. Why do you think the penumbral eclipses would not be very important? Well, the reason why is because if you're in the penumbra, then the Earth is only partially blocking the sun. So say it's blocking half the sun. Well, half the sun is still a lot of light. And while penumbral eclipses happen quite frequently, they're not noticeable. I mean, if you were to look at the moon, you wouldn't be able to tell that a penumbral eclipse is happening. Maybe if you had some device that can actually measure how much light is being reflected off the moon, maybe you could determine that, but it's not something that's easily seen with the eye. Right? So it's all about the umbra. All about the umbra. Question for you here. What phase must the moon be in for a lunar eclipse to occur? Right? The phase must be B, full moon. That's full moon, so that means the moon and the sun have to be on the complete opposite sides of the Earth, and that's the only place that eclipses can occur because shadows are on the opposite side of the Earth. So in no other phase would the moon be near a shadow for that to occur. So it has to occur during full moons, which means, you could have them at the most frequent occurrence of full moon of lunar eclipses would be how often full moons occur, which is once a month. But it's never once a month, actually. We'll get to that in a moment here. All right, so this is a picture of a total lunar eclipse. It's when the moon completely enters into the umbra. You might notice that it's not totally dark. In fact, it takes on a reddish tint, and it's something that we refer to as the blood moon. And a partial lunar eclipse, as you see in this picture here, is when the moon partially gets into the umbra, and we can see the shadow of the Earth in the bottom right here. Again, you can see the curvature to the shadow. So the moon is not totally in the umbra, it's just partially in the umbra. And those are the distinction between the two. Now, this was actually an eclipse that happened way back in February of 2008. It was a near total lunar eclipse. I say near because there was a tiny, tiny little sliver at the top that actually didn't quite get completely into the umbra, but it like over 95% of it did. So you can see the progression. We're seeing a full moon, and then you see the moon is starting to drift into the umbra, and at some point it kind of gets all the way in there. And then it takes a reddish tint to it here. I'll explain this reddish tint in a minute. The amount of time that this takes can be a couple hours, maybe 3 hours for this to occur. This was a neat one. Just I remember very well, just because it was it happened like at 9 p.m. on this particular day, which is a very convenient time to view an eclipse. Sometimes eclipses happen at 3 a.m. and I love astronomy, but I don't 3 a.m. love astronomy. I'm going to be in bed for that eclipse, unfortunately. So, all right. So this is a kind of a bigger picture of this blood moon here. The totality of the eclipse can be quite long. It can almost be like an hour and a half or so. And the red that you see here, okay, so the moon doesn't totally disappear. It is awfully faint. I mean, if you look at this picture here, I mean, it's a little exaggerated, I would say, in this picture, actually. The reddish tint is very, very mild, and it's very exaggerated in this picture. This is like it's like a long exposure photograph to highlight the red in there. So what's happening here is no direct sunlight can hit the moon. No direct sunlight can hit the moon because the Earth's in the way. But light can glance by the Earth and pass through the atmosphere where it gets filtered. Sunlight is filtered in our atmosphere. That's why the sky is blue, because sunlight is filtered and the blues and greens are taken out to a greater extent. So we have a blue sky because of that. And then the light that's left over is sort of more preferentially like red, orange. Well, it's filtered and it's scattered. So while the light doesn't directly hit the moon, it can get scattered in the atmosphere of the Earth, and then it hits the moon. Then it bounces off the moon and we see it. So what you are seeing is you're seeing this filtered, reflected sunlight that has passed through the atmosphere and has indirectly hit the moon and then comes at us. And that's why we get the blood moon effect, right? It's kind of similar to when you see like the moon on the horizon and it looks very deep, kind of orange and red. But in the eclipse case, the orange and red is actually the color of the moon. It actually looks that way. Whereas on the horizon, the filtering is happening after the light bounces off the moon. So when we see it, we're seeing the after filtering. Whereas the filtering in the eclipse is occurring before the light reflects off the moon. So there's a slight difference there, but the red is due to the same effects. Okay. So this is data that I grabbed from NASA. When it comes to eclipses, whether it's solar or lunar, there's really only one source of information for this stuff, and it's NASA. Nobody else really does the extensive research that NASA does to figure these things out. So I grabbed this from the NASA page. You can easily find this if you just type in NASA lunar eclipses. You'll be taken to the main page for NASA, and what we're seeing here are the eclipses that are going to take place over the course of the 2020s. And when you look at this, there's a few things to keep in mind here. First thing you want to take notice of is the time. Now, the time is given in UT time. And UT time, universal time, is time that's about generally 8 hours ahead of Pacific time, where I'm recording this from, the west coast of the United States. So you take these times and you subtract off 8 hours. And then you ask yourself, if I subtract off 8 hours, is that daytime or is that nighttime? So like, you see this one on November 8th, 2022, it says 11, right? Subtract off 8 hours from that, and you get something that's like, what, 3 a.m.? That's nighttime. So, yeah, you can see it. But it's 3 a.m., so good luck with 3 a.m. That's rough. Okay, anyway. But some are more convenient on here, like the one in May that's right above it. So that was 4 a.m., but then again, subtract off 8 hours, so that's like almost 8 p.m. the previous day. That's beautiful to see, right? That's really nice to see. So yeah, you can do that. Now, we have daylight savings in California, so if it's daylight savings, you got to do 7 hours instead of 8. But you get the picture, right? So that's how you know if you can see these things, and they kind of give you a general idea of what regions can see these eclipses. But you're looking for, you really want to see a total. I mean, partials are okay; they're just not as impressive. If it says penumbral, ignore it. You're not going to see a thing, right? So, yeah, you can see here with the ones that are coming up here. So subtract off 8 hours. If it's nighttime, yeah, it's something you can see. Go check it out. One last thing to notice about this table here is if you look at the calendar dates of the eclipses, you might notice an interesting pattern that shows up here. So at the top we have May, and then after that, November, then May, then November, then May, then October, then March. It's about 6 months apart, these eclipses. So just take note of that. We're going to get into solar eclipses here, and then we're going to see that same kind of behavior in the solar eclipses, and then we'll talk about what the meaning behind all that is. All right, so we're going to get into solar eclipses here, and something really unique and special about solar eclipses. Now, you might remember I had worked out in a previous lecture, and then I assigned as a homework problem trying to determine the angular size of the moon and the sun. And that's done with the small angle formula. How large something appears is based on how large it is and how far away it is. And when you did these two calculations, and this is one of the reasons why I had you do the calculations to see for yourself, is that the moon and the sun have almost exactly the same angular size. They almost look exactly the same size in the sky. It's about half a degree. And there's no particular reason why this exists. We know in the past it wasn't true. The moon was closer and therefore larger. As far as we can tell, this is just an amazing coincidence. But because they are so similar in their angular size, the way that the moon blocks the sun can vary slightly based on the exact angular sizes of these two things. So this picture here is showing a total solar eclipse. Now I say sort of total solar eclipse. The reason why I'm saying that is because you see the umbra and the penumbra shadows here, and they hit a particular region on the Earth. Now, if you're in North America, you're not seeing an eclipse, right? If you're in Brazil, according to this picture, you're most likely seeing a partial solar eclipse. And there's a small portion where the umbra actually does hit the Earth, and that's where the total eclipse would actually be taking place. So, lunar eclipses are a bit easier because if you want to see a lunar eclipse, the only criteria needs to be, is it nighttime? Anybody that has nighttime can see the eclipse, but for the solar eclipse, the shadow of the moon is quite small, and so when a solar eclipse is going to happen, you have to be in the right place for that. You can't just be anywhere on the Earth. So now, here's an example of a total solar eclipse. This is one where the angular size of the moon was sufficiently large enough to completely cover up the sun. And they're showing the progression of the eclipse on the left there. Just to let you know, that progression of the eclipse can take maybe like an hour or so, like totality, where like the moon's completely covering the sun. It can be about 5 minutes or so at most. But the whole pass in front of the sun could take a bit of time, an hour, 2 hours or so. Yeah, 2 hours is pretty average for that. What's kind of neat in this picture here is this picture was taken during totality, and the moon was able to sufficiently cover up the sun, and so we can't see any surface of the sun. But what's poking out around the moon is the atmosphere of the sun. And so these eclipses give us this really unique opportunity to study the atmospheric effects of the sun. We're seeing chromosphere and corona. Those are two different atmospheric layers of the sun. When we talk about the sun later on in the class, I'll talk more about these. You see some prominences there, which are kind of like solar flares, but not eruptive. But hot gas coming up off the surface is easily visible in this picture here. So this is it's a really unique opportunity to see this stuff. A couple other phenomenon that happen during solar eclipses that are really neat. The one on the left is called Baily's beads, and it's caused by the fact that the moon has different levels of elevation because of things like mountains and hills and craters and stuff like that. So when the very last little bits of the sun start getting covered up, you actually will start to see these little beads, and the beads again are caused because there's different elevations of land, and so different parts of the sun are getting covered up, and that creates that bead effect. And then the really neat effect that takes place is called the diamond ring effect, and that's what you see on the right hand side there. This is when like the very last little bead of light gets covered up. It kind of does this big flash, and due to the nature of the eclipse, it looks kind of like a ring. At least see the round part of the ring, and then the sun looks like the jewel. And actually, the sunlight does kind of change colors. There's an optical effect that changes the colors of that bead, and so it kind of does resemble like a diamond jewel. So it's kind of a neat thing. Now, by the way, just to be super, super clear about this, these kind of things, you don't view with your eye. Right? The viewing the sun with your naked eye is extraordinarily dangerous, and so make sure you have proper eclipse glasses. You can buy it for like $1 per glasses on something like Amazon or something. But these kind of effects, these were taken with cameras that had proper block-in filters that make the light a lot less dim. So just make sure you're always wearing protection when you are trying to view eclipse effects, because your eyes can get really, really, really damaged by looking at this stuff. All right, so I mentioned stuff about the angular size. I said that there are both about half a degree, but they do vary a little bit. Okay, so remember that as the Earth orbits the sun, there are these two positions in the orbit called perihelion and aphelion, closer to the sun, farther from the sun. And so while the angular size of the sun may be about half a degree, at perihelion it looks a little bit bigger, and at aphelion it looks a little bit smaller. Likewise, the moon in its orbit has similar positions too. We call them perigee, and we call the other one apogee, closer to Earth and farther from Earth. Same deal. When the moon is near perigee, it can look a little bit bigger, and when it's at apogee, it looks a little bit smaller. Again, about half a degree. But when eclipses happen, the Earth could be at any place in its orbit, and the moon could be at any place in its orbit. And so we have to really know what the precise distances are to determine the kind of eclipse that are going to take place. So what you see at the upper left here are the relative angular sizes of the moon and the sun. Now, the moon has a greater variation in its distance, so there's a greater variation in how it will appear to us. Earth has less of a variation in its orbit, so the sun doesn't vary as much as the moon. But while all of these are about half a degree, there's a little bit of difference again because of distance. So if the moon is at perigee, for example, moon's going to be sufficiently big enough to cover up the sun no matter where the Earth is located. And there can be a total eclipse at that moment. But let's say the moon is closer to apogee. and it's much smaller. And then maybe it's around wintertime and we're at perihelion, and you can see there that the moon is not sufficient to cover up the entire sun. And if it tries to, we get the effect that we see at the bottom here. It's called an annular solar eclipse. Annular referring to the fact that the appearance of the sun, it's like a ring around the moon. And, the moon just can't completely cover up the sun, so we call this an annular solar eclipse. It's a type of partial eclipse. You could have totals if the moon's big enough, or you have partials. And sometimes the partial eclipse happens because the moon is completely in the sun, like in the disk of the sun. And that's what's occurring in the picture here. And of course, same deal. If you're trying to observe something like this, you got to be using eye protection to make sure you don't, hurt your eyes when you're looking at this stuff. But yeah, sometimes eclipses can be annular, just based on how the distances go. This is the NASA eclipse page for solar eclipses. Now, not sure when you're watching this video. It could be far into the future, but I'm recording this in 2024, and we just recently had a couple of partial eclipses. We had the one in April. That was a total eclipse, and for us in California, we saw about 60% coverage or so of the sun. And then the one before that was an annular eclipse, and that was the one on October 14th. Occurred around the same time as the other one did. This one peaked in like Texas, so we still saw a partial here, but it was still really impressive. Even though it's 60% coverage, you still got 40% sunlight. You still notice a lot of effects, a lot of things happening. You notice like the air gets cooler, actually. You notice things are darker. Shadows change. Because generally a shadow takes on the appearance of the obscuring object. But if the light source isn't uniform, like an eclipsed sun, then the shadow actually takes on the appearance of the light source. So it's kind of crazy. You can look at the shadow of like a tree and all the leaves will look like crescent leaves. And it's kind of like surreal when you see that. It's just not really expected. But, I believe we're, at least in North America, we're not going to have a real good total eclipse for a while. I don't think it's happening until like the late 2040s or something like that. So yeah, we got lucky. We had several. We had one back in 2017. We had these two recently, but nothing too dramatic coming up here. Unless you want to travel. If you want to go somewhere, you go to Greenland. You want to go to Greenland? You want to go to Iceland? Let's go to Spain. I think that Spain's a little bit nicer than Greenland, I think. No offense, Greenland. But August 12th, 2026? That sounds like a plan. That's the next total. All right, look at the dates. June, December, April, October, April, October, April, October. 6 months apart, 6 months apart, 6 months apart. Same kind of pattern we saw with the moon. So that's interesting. Here's a question for you. Solar eclipses can only happen when the moon is in new phase. Why don't solar eclipses therefore happen every month when the moon reaches new phase? So look over these options. The answer here is D. Remember that orbital tilt that we saw at the beginning of this video? Because of the orbital tilt, the moon's position can be above or below the ecliptic, which means it will miss shadows. Shadows will miss, and then there's no opportunity for an eclipse. If the moon did not have a tilted orbit, we would get eclipses every single month. But now we can only get the eclipses when the moon gets near the ecliptic. And that can really only happen once every 6 months. Okay, this picture is a good illustration of what's going on here. If you look on the bottom left or the upper right, because of the tilt of the moon's orbit, we're seeing shadows that are going to miss. Now, in the moon's orbit, there are these two locations where the moon's orbit intersects the ecliptic. We call them nodes. And if we draw a line between the nodes that goes through the Earth, we call that the line of nodes. And if the line of nodes points at the sun, that means the positions where eclipses can occur are right in front of the sun or right behind the Earth. So if the moon is in a node, when the line of nodes line up, that's when you can get an eclipse. So you can see that's only 6 months. Upper left, the bottom right, that's opposite sides of our orbit. That's 6 months apart. So that's, there is a possibility though. Like, if you go back here, let me see. Let's look at this chart again. Sometimes you get these back-to-back ones. Yeah, like if you look at the bottom here, 2029, you get a June and a July one. It is possible that you can get a back-to-back one because, the line of nodes, it's not like a single day that it lines up. It could be over the course of a month that it lines up. So you could maybe right when the line of nodes lines up, you get an eclipse. And then by the time the next phase happens, where there could be another eclipse, the line of nodes is still basically pointing at the sun, so you could actually sneak another one in there. That's a possibility. But that's why these things don't occur as frequently as they might in other circumstances if the moon didn't have a tilted orbit. Okay, I believe that is the end of this video. So I hope you have a great rest of your day.